I've already written out the continuous time evolution operator. So now imagine that there is a deterministic trajectory which is obtained by integrating the velocity field that defines the dynamical system, and in finite time it produces this finite forward time map. And that depends on the point on trajectory and the time on trajectory where it started, and it lands someplace else. Then it's very natural for us to change coordinates and write this as parallel coordinate. We have an orbit. And instead of using our Cartesian coordinates, x1, x2, x3, at every point of the orbit, we produce transverse coordinates and one longitudinal coordinate which measures curvilinear Euclidean distance and whatever metric we are along the orbit. So this is one-dimensional, and our evolution law now says I start in full dimension of the space x at time t1. I run and I take only the parallel component, it's the only component that's along the direction of this new curvilinear coordinate system, and I end up at t2. So that's one dimension of the delta function. And then there is the remainder, which we'll call transverse. And that's d minus 1 coordinates in transverse directions, measured at time t2. The transverse coordinates of the map depending on the full position in the space, both longitudinal and transverse. Now we are trying to get rid of time because time is very awkward. Because what we need to impose is that the difference between these two times is the time that eloped in the evolution in between. So what we do is we change the coordinates from time, which is one possible parameterization of curve is curvilinear distance, and the other parameterization is time, fixed in time, and they're related by Jacobian, which is now one-dimensional, which is simply the magnitude of the velocity time t. This time here minus the difference final and initial. What we want to do is we want to integrate over all times. There could be other ways, but it seems very natural. Is to penalize long times by putting a Laplace transform kernel here. And now we have a integration of all initial condition, which is split up in this now curvilinear system, and we only need to integrate because it's a delta function in an infinitesimal neighborhood of this trajectory, so there is no global problem of constructing this coordinate system. You just construct it in a place along the trajectory. And we have isolated the longitudinal or parallel coordinate in it. And now what we have is, from here, we have 1 over e, which means velocity at position xt. And then there is this integral, which is the parallel one, but now it's just written as integral in time. And there is the transfer thing, which I will not write, but it does depend on the time. So now what happens is that this Jacobian, which we computed going from spatial coordinates to parametrization by time, so this is dimensions of length over time, is precisely the same Jacobian I need in integral. I can move this integration, time integration in, perform it. And what this integration now gives me, it gives me only contribution when I have a periodic orbit, or its repeat. The contribution it gives me is E2 minus S, the length of periodic orbit, times R, because that's the only time this thing kicks in, because that's the only time when my position along the orbit works out. And then the integral in the neighborhood and longitudinal direction is taken care of. I find out that for periodic orbits, I only have to integrate over, the orbit is compact. So my longitudinal integration is only over one repeat of the orbit. And this thing, when I go to time coordinates, gives me a period TP. And then there is still integral to do in the transverse coordinate. Is the transverse function, but now it depends on R and TP. Gets contribution only for points which are on a periodic orbit, and only for mappings forward which are one return. It repeats. So wonderful thing has now happened. Contributions are all invariant. And to convince us of they're invariant, we have to compute this Jacobian and show that this was invariant on a periodic orbit. That's the eigenvalues of this Jacobian invariant. They all have compact support because they're computed on periodic orbit, which is a finite loop in space. So even though we are looking from 0 to infinity to infinite trajectories, the result is now the sum of invariant contributions, all computable in finite time. It's this integral that's now left. This is the integral over longitudinal coordinate. I'll still have to do the transverse integral. The only remnant of my reconstruction equation that said that this can only work if the time labels line up correctly, satisfy a correct condition. The only remnant that is this sum of characters. On any piece of trajectory, there is no invariance at the time because this law is constantly changing as we move around. But after averaging over all times, we get contributions, all of them which are time independent and position independent. And we get a beautiful general answer.